Hello, today is October 31st. It's around 11:23 p.m. Central Standard Time, Central Daylight Time. I'm Bhavani from the University of Texas at Dallas. I'm sorry I'm unable to be in person to give this presentation because of a family personal situation. And so I'm recording this presentation, and it will be played at the conference. This is the special session on Vision Track. And so I believe there are about 6 presentations, and we are allocated total of 2 hours and 15 minutes, which is around 135 minutes. And so I'm going to try my best to finish the presentation in 25 minutes, because I think if you divide it by 6, each person gets about 25 minutes. So, okay, so my talk is on securing multimedia data systems in the era of artificial intelligence. And I'll talk about the past progress. Tremendous progress has been made starting from around 1990 until today. So many people, sort of forget about the past. And I worked in cybersecurity since 1985. So for about 38 years, fall of 1985. So I want to give the past and then talk about what are some of the challenges and our current research and the directions. Okay, so I'm going to share my screen. Okay, so securing multimedia data systems in the era of artificial intelligence. I'm going to go through this fairly quickly because of the lack of, because of the, short time period, about 25 minutes. And also, it's sort of shaking a little bit because I'm in a hotel room, and there's no desk here actually. So I am, seated in this chair with this laptop on my lap. So anyway, so very briefly, I'll talk about multimedia data management systems, past progress. It was actually based on object data models, and then talk about access control, build a Padula model for multi-level security. And also some of the more recent work, more like 10 years ago, on secure multimedia and geospatial systems. And much of the current work, on securing multimedia, it focuses on artificial intelligence or machine learning. So why multimedia? Because, you need persistent storage for managing large quantities of multimedia data, right? So Multimedia Data Manager manages various types of media, text, images, audio, animation, video, and even sensor data. And, when you combine different types of data, so these multimedia data is sort of increased, the various types are increasing and extended by a browser to produce hypermedia systems. And heterogeneity with respect to data types and numerous applications. We know entertainment, defense, telecommunications, financial, medical, you name it, because we use video almost all the time these days. Even right now, we are using video and audio combined together. It's all very smooth now. But when I started working in multimedia, actually around 1988, it was really very sort of very sketchy and rather vague. You couldn't put video and audio together. You got to separate the multimedia with the metadata. Even database systems were not tightly integrated. So it was a challenge at that time. And now so many advances, but still there's so much to be done. Okay, so back in the early days, when I say early, about 30 years ago, for multimedia systems, we focused on representing multimedia data as objects, right? But these days we are using XML and all kinds of data types. So in an object model, every entity is an object. It could be a book, a film, an employee, a car. And then objects are grouped into classes. And the classes have attributes or instance variables, and you have class hierarchy, parent, child, and you also have, there's a lot of work on composite objects, composing different video, composing different text, and so on. And then, of course, methods are functions associated with a class. So update objects, you've got to execute methods. And now it's sort of common practice now, right? In Java, so many programming languages based on object models. But at that time, it was really, quite challenging. So a lot of the work in multimedia, based on objects is access control, right? On classes, attributes, and so on. And execute permissions are on methods. And then, of course, a lot of work on multi-level security. That's the military type security that I was involved. And security impact on class hierarchies and security on composite objects. So before I go further, objects and security, overall, there was a lot of work starting around 1990, and it's still ongoing with object management group, but now we are including several other features, right? Web services and service-oriented architectures based on objects, and also, with AI systems where underlying technology is really still based on, I would say, objects. So my work was focusing on object-oriented databases and developing object models, as well as object-oriented design and analysis and secure distributed object models. But then there was also work on secure programming, object programming languages, frameworks, and so on. And of course, everything is unified with object modeling techniques. So I'll just focus on the data management aspects, what we did for securing data systems. Okay, so on the left-hand side, you have employee class. Right-hand side, it's a department class. Please don't worry about the shading, because one is shaded white, the other one is yellow. No particular reason, just that when I copied from a paper, from one of my papers, and put into this presentation, the white part didn't get copied. So anyway, so we had, so the object-oriented access control models. John has update access to a particular class, read access to another class, and Jane has update access to a particular object with object ID 500, and Mary has execute access to increase salary. So again, increase salary, you have an object ID and value, you read the salary, increase it by the amount, and amount by value, and that's a new salary. So you execute the methods in order to update the objects, right? So certain people have certain permissions. So some pioneers for discretionary security, I think their paper appeared around 1990, was Elisa Bertino when she was at MCC, focusing on securing object models, and her focus was on discretionary security. And then for the composite objects, of course, you have, say, employee has manager class. So for instance, John has update access to employees and read access to manager. But for a composite object, you can say like John has update access to introduction and references, and John has read access to set of sections. So object, so even typically a multimedia object is composed into multiple smaller objects, right? Smaller objects are composed into forming a larger object. So you have grant permission to different parts of the object. So in terms of discretionary security, I think I would say the main work was on Orion, which is the MCC. There was a consortium in Austin, Texas, and Elisa and Won Kim and their colleagues developed a discretionary security model. And also there were various commercial products from HP and Serviologic and so on. At that time, we really thought, right, in the early 90s, that object-oriented systems, database systems are going to take over the world. What happened in the end was relational database like Oracle, they started incorporating objects and supporting multimedia data. Okay, so multi-level security, of course, we use the Bella-Padula model, a slight variation, read at or below your level and write at your level. So we developed prototype systems, and some of our work went into commercial products at that time. Ontos, Air Force was funding, Navy was funding our work, and Air Force was funding these commercial companies, and Air Force had funded some of our previous work, and so some of this work, it went into Ontos database systems. So you have a book where introduction is unclassified, but set of sections and references are secret. And so certain people have, top secret and secretly cleared users can have access to set of sections, and that's top secret, very dark circle. And secret is references. So all the sections are top secret, references are secret, and introduction unclassified. So you read at or below your level and you write at your level. So top secret user can read both unclassified and secret and top secret and so on, okay? So some security properties we developed. Again, read at or below your level, write at your level. It's a variation of Bella-Padula model. So the properties were security level of an instance must dominate the security level of the class, because if the whole class is classified, right, if we cannot see any information about departments, then it doesn't make any sense to have access to a particular department, right? So those were the properties we came up with. Security level of an instance must dominate, security level of a subclass must dominate the security level of the class. And classifying associations between objects, right? The objects could be unclassified, but there's an association between them is classified. And then methods that execute at a level that dominate the level of the method itself. So these were a lot of properties that we developed, and a formal model, and then we had to also, a model, informal model, and then a formal model. So very briefly, some sample multi-level secure systems, and I was involved in actually 3 of them. So there was a Sorion, which I took Elisa and her colleagues' work at MCC, Orion model, and that was one of the early work on incorporating security into that model, okay? So SO2 is also my work, where we took that O2 from France, INRIA, and then incorporated security. And then Teresa Lunt and John Millen, they came up with their model. And I was also an adjunct professor when I was at Honeywell. That was the first system, actually, was SODA. And then I developed another system called Orion. So these early works were published actually in 1988. And then later, Sorion was in 1989 at the Uppsala conference. So then Morgenstern at SRI came up with this model. And then at MITRE, we had funding from the Navy to develop the UFOS model. So I was involved in that as well. So I was involved in Sorion, SO2, SODA, and UFOS. And then Jajodia and Kogan, they came up with their model based on message passing. So it was very popular at that time. So then what we did, so our interest in objects was twofold. One, to secure object model and use objects as the basis for multimedia systems. And so our architecture, we assumed a tight architecture, and I'll show you the prototype also we developed securing that system. So you have a multimedia data manager integrated with the metadata. Right? That's a tight integration at the time. We have a multimedia database. We had video, audio, and text, and images, and then, of course, the user interface. So the access control model that we developed, okay, granularity of protection. So John has access to certain chapters. That's a discretionary. Images, John has access to portions of the image, access control for pixels, and the video, John has access to frames 1000 to 2000, and John has access only to the scenes in the US and various security. We call them security constraints, but these days we call them security policies, right? They're more or less, they're exactly the same thing. So collections of images, when you put it together, like they become classified, okay? So this is the integrity lock approach that we designed and implemented. And so it's kind of interesting because we took the systems for relational and we implemented them for object systems. Okay, I have got to tell you though, when I say fully implemented, it was sort of simulating, right? Because we didn't really have a trusted platform, right? So we had simulating. So we have a trusted computing agent. So all the input requests come to the agent, and then they would compute a checksum. So video encryption or image encryption, whatever, right? And then you take the checksum, compute a security label. So from the checksum, say 1538, security label is say secret or whatever, you take it, and we keep the data manager untrusted, and then we store that data together with the checksum, right, and the label. So when a user wants to retrieve, right, on the way out, what the trusted agent does is processes the query, gets the result, and it has all the information, the checksum, right? It compares the checksum, what is stored, with the checksum, it recomputes. If they both match, that means it's valid. You can give it to the user. If they don't match, that means the data might have been tampered with. Something has gone wrong. And so data might be still fine, but the labels, somebody might have corrupted, so you don't give that information to the user. So we took the integrity lock approach, and then we implemented it. When I say implement, it was not full security, it was simulation, the security features to show our customers, our sponsors. Okay. And then I also looked at inference control, where you have collections of data together, and it's highly classified. Individually, they are unclassified. And so, and also another thing is that, right, I mean, logical inference, if A implies B, from looking at one video, you know what the other video is. The second video is secret, so the first video has to be unclassified. So we developed an inference controller. Unfortunately, we have a technical report, but our paper was accepted, and the student, I think it was International Journal of Security and Privacy, the student, we couldn't contact him for the signature, and then I kind of dropped the ball on that. So we just have a technical report on this, where we implemented inference controllers for multimedia data management systems. Okay. So then around, latter part of 2000, the 2000s, Elisa, myself, and Michael Gertz, we explored jointly geospatial data. Again, there were some customers who were interested, so we wanted to do some initial work. And so geospatial images could be raster images, that store images, pixels, digital vector images. It's sort of imagery data, which we consider to be multimedia. So there's a GSAM authorization model, specifies subjects, credentials, objects, like points, lines, pixels, and the access that subjects have to object. And we published a paper. It was a top-tier paper. I think it's ACM Geospatial System Conference. And so some of our findings, security and privacy for geospatial data. It was sort of a high level, but it was a very interesting paper. And this was our geospatial architecture. So we used the Open Geospatial Consortium, OGC framework. We even presented our results, some of our results at OGC. Core Application Schemes is a standards organization, geospatial features, and so on. And of course, we use GIS web services and traditional GIS wrappers. Security layer is what we designed. And some parts we focused on, in particular, DAC, RBAC policy, and then add other things we added in the design, like authentic data publication, auditing, misuse detection, policy reasoning engine, and trust and privacy management. And of course, access control model is central. And then at the bottom, we have the data layer. We have the data registration and integration and repository services, right? So your data layer, and then your security layer, and then comes the sort of the user interface type of layer. Okay, and then based on this, right, we came up with lots of policies, and I'm only going to give you a sample. We had content-based policies, context-based policies, and so on. So one type of policy is active policies. What are they? They are policies that, when applied to a protected object, perform certain transformations on the object. So certain people have authorizations to do transformations before returning to the requester. Two relevant cases are filtering policies and the obfuscating policies. Filtering policies refer to policies that filter out some portions of the object before returning them to the users. Obfuscate, of course, as the name implies, the policies act like filter policies, except that they do not simply select objects, but perform possibly complex computations on the features to be returned, right? So they can, obfuscate certain things. So typical examples include computing a lower resolution image and distorting some vector data, but preserving the topological relationships. We tested this on some data that UC Davis had about some land data, and we tested some of these policies on that. One can even specify policies that return incorrect data, honeypot in the context of misuse detection. So you can see, so obfuscate, and so on. So there are other policies where you can merge and you can edit, and access is given based on, users' roles and so on. Okay. So then, of course, coming up with this is the policy language associated. So GML, Geospatial Markup Language, I believe it was OGC's work. And take a security model language extended for geospatial. Elisa Bertino has done a lot of work on XACML and GeoXACML. And then Bertino and her colleagues also developed, it has several citations, GeoRBAC. And then we looked at semantic web languages at UT Dallas. And one of my students developed GRDF, RDF for geospatial data, and then security constructs. And we presented this work at OGC. And that was back, I think, in 2006, 2007 timeframe. Okay, so a lot of other work, and I won't go into it because I want to go to some of the current directions. Multimedia and geospatial data mining, security and privacy, data privacy for multimedia systems, image and video data privacy. There's also some work on privacy-aware video data privacy. That we did some work on that, and it proved to be, it was quite challenging to do that, at that time at least. Then we were very successful in coming up with video surveillance. That's not really cybersecurity, video surveillance for counterterrorism applications. And we had quite a few papers on that topic. Again, privacy. So if you are applying it for counterterrorism, then you need privacy-aware video surveillance, right? And then there's biometrics, security and privacy. And then I applied, as I said, inference for multimedia. And there was some other high-level work we did. We had done a lot of work on real-time and multimedia. How do you bring in security, real-time, and multimedia? So one thing that was really my dream, and we couldn't do it, was to combine some of these things, right? We had a face detection project, one of my students did, and then video surveillance, and then we wanted privacy. So how do you give privacy? So we said that we encrypt everyone's faces, and if they do something suspicious, that's our video surveillance project, then you decrypt for those people. And so we presented it to some of our government sponsors. They said it won't fly if we have to encrypt everyone when we are outside, right? So we had these different pieces, and we didn't complete that project integrating all these different pieces. Okay, so currently our work, and this is where the future is, and we got to bring in the multimedia because there's so much video, audio, images, and so on, sensor data, right? So this was with Murat Kantajulu and Elisa Bertino and quite a few others too on this project, where we said that there's a lot of information being collected, health, fitness, location, social media, image, video, so a lot in multimedia format. And so we said that policies have to, so there was a quantified self approach, self project by sociologists and psychologists. So what did they do? They looked at, all the help that you can give individuals, right? Look at, learn about the individual's behavior patterns and their preferences. If they like chocolates, then you tell them don't eat chocolates, right? Know everything about the individuals and then give them advice. Yes, it's great, but the privacy could be violated because so much data is being collected. So what did we do? We said everything has to be governed by policies, right? So we have our smartphone or iPhone, Android, whatever. So we have data collection, policies governing data storage and access policies, analytics, everything, and data sharing, all governed by policies. Some of the data goes into the cloud, and some, through cloud-based services, you can access the cloud. So we developed, the design was to privacy-aware, policy-based quantified managers. So we are saying policies. You need data collection policies, data storage policies, data analytics policies, data sharing policies. And so we presented this work at ACM SACMAT. And that was around, I think 5 years ago. And so this is really what the design of the system. We had a mobile device with all these applications and then the encrypted cloud-based encrypted store. So the rationale is a lot of data being collected, right? Based on the access control policies, running on devices will be given access to some of the collected data, right? Some cases, we don't have to collect, there'll be so much data. If you're 20 years old, right? You eat, say, big meal, and then, okay, you could put on 5 pounds overnight, but it's not a big deal, especially if you're 20. If you're 70 or 80, then if you put on 5 pounds, your heart could give, it could give up. So those are the things. You don't want to store everything, but some things. And the worry we have is that if this private data goes to insurance companies, that, your healthcare, that you have diabetes or something, healthcare could be, denied, not just to your children, not to you, your children and grandchildren, right? So, and again, based on different scenarios, some data could be fully encrypted, some no encryption, some partially encrypted. Okay, so this was a very interesting project, and this is really privacy. So it brings privacy, machine learning, and the policy-based approach. Okay, another thing that we are doing, and this is with Professor Latifa Khan, where we have a lot of streaming data, and video is streaming, right? A lot of videos are coming, animation maybe, and also sensor data. It's streaming. So we developed, machine learning models, use past data to build classification, products label future instances, and helps decision making. You might ask, what's the big deal? The big deal is data streams, massive amounts of data. Concepts are changing. Back in the old days, when we did machine learning, only one model, but now we have multiple models. That's very common in our digital world. So you have the firewall, right? You have attack data coming in, and then you have model updates, and benign traffic goes in here, attack traffic, you quarantine. So the challenge we have here is that how do you develop these multiple models? You can't have infinite number of models. Some modules get outdated, right? So today it could be go and see this movie. Tomorrow it could be another movie, or buy Microsoft stock, or tomorrow it's going to be by Google. So things are changing. So we build multiple models, and then we throw away the models that are no longer valid, right? So that was really Latifa Khan's kind of brainchild, because he was one of the pioneers, together with Jay Han, and I was sort of part of the project. And so this was some very interesting. Now the challenge for us right now is to look at multimedia data. And Latifa and his PhD student, they had done a lot of work on machine learning on images, as machine learning on video. So how do you apply security, and what about privacy issues? Okay, that's the challenge we are faced with. And so our work, we applied it to inside a thread. So a person here is going to be typing in all these words, and so you have you use chunks and extract features, and then of course build an ensemble of models, and then you apply. Sorry that it got a little bit. I copied from another presentation, so it got a little bit distorted. Learning algorithms, we did supervised as well as unsupervised. And so automatically the models will talk to each other and throw away the models we had an algorithm that are no longer useful. And then of course, when the chunk I+1 arrives, right, you extract the features, there's a testing. And then based on what you have learned, right, is it an anomaly or not, right, inside the threat or not? But we were working with streaming data, right? But now what about so many videos are coming in, and are the videos, are they genuine, or are they being attacked? Are they being manipulated? So it's a very good application when you bring in multimedia and AI. And so this is Dr. Murat Kantarjalu, and it's actually his brainchild. And we were one of the early people to look at adversarial machine learning as early, this was like 10 years ago. He's continuing to work in that area. And so this is sort of I call it blue line, but again, when I cut from another presentation and I pasted it here, it is turning to be a yellow line. Essentially what we are doing is, this is not about concept drift, right? And many of you all would know about this. It's not online learning. Adversary adapts to avoid being detected, right? So it becomes a game playing. We try to sort of outsmart the adversary. Adversary tries to outsmart us. So it becomes a game between us and the adversary. So you can see, this is the support vector machine boundary line, right? So the red crosses are bad instances. The yellowish circles are good instances, whatever is shown here. And so the adversary is trying to push the red to make it good, right? So we have 1, 2, 3, 4, 5 of them. The bad instances are now good instances because they have found out our models or poison our data or whatever. So this is the challenge that we are faced with. So what do we do? And I'm sorry, I haven't pasted that photograph, that picture. So what we are trying to do, our solution, which I haven't shown here, is move this support vector machine line, move it further, right? So we published this paper, by the way, in ACM KDD. So when we push it further, then, sorry, not further. What I meant was we push it in this picture, we push it down so that the red instances, like the two red instances, would not be detected, right? So we modify the support vector machine line. But you can ask the question, we can modify it so that we can modify it right up to here. So all the bad instances are detected. But what happens here, if you do that, the red, the yellow circles, the good instances, will also be shown as bad instances. Okay, so we don't want false positives, we don't want false negatives, and so there's a lot of mathematics involved in coming up with the right place where to push this support vector machine boundary line. So that was the challenge, and we solved the problem and presented it at ACM-KDD. And I think we also had another paper on adversarial decision trees. And then Murat Kartajulu did, several pieces of work in this area. And I think this is important for multimedia because video data could be attacked, right? Audio data, it becomes that much more complicated. Image data could be attacked. And so how do you have adversarial machine learning for multimedia data? There's already some work, preliminary work going on, so others are looking into it. And this is really a major direction. So where we are going next is we are part of this very large $20 million US Department of Transportation Center in Cybersecurity. Clemson is leading it, and UT Dallas is part of it, together with some other universities like Purdue, UC Santa Cruz, and also University of Alabama and Morgan State University. And so it's a very exciting project on Internet of Transportation, right? Cars, you have the Internet of Things at home, right? Your television talking to your microwave, talking to your clock, and so on. And here what's happening is the cars talking to the trucks, and trucks talking to the, trucks and the trains. And so it's not just land vehicles, also sea vehicles and, air vehicles, like drones. So what about security, and how do you bring in sort of machine learning / AI? When I say AI, for me, it's mostly machine learning and the transportation systems and security. How do you integrate it together? And so the three principles from our end, I'm the PI, and Murat is a major player focusing on, he's heading the data privacy subtrust, and Latifa is focusing on, in general, the machine learning and the data security. He's focusing in that area. So, and also Murat is focusing on risk. So three of us are, we work together as a team. So that's where at least my research for the next several years will be focusing on how do you bring in multimedia and AI and AI/ML, and of course, security and privacy. So that's where I'm going to stop, because I think my time's up. More than hopefully I didn't go more than 25 minutes. So there's a lot of, I talked about the early research more because many people sort of these days forget where we came from, right? And so, in data security, or in security, privacy, trust, and so on, we've been working, especially on the security part, since the 1970s with the Hinke-Schaefer model. So we are looking at about 50 years, or about 45 years. And then, multimedia security, we've been working in that area for about 35 years now. And now, of course, bringing in AI and so on. How do you bring all of that with deep learning? So there's a lot of opportunities and a lot of challenges. So that's the message I want to give in this presentation. And again, sorry, I was not able to, let's see, I'm going to now stop sharing. How do I stop sharing? Okay. Yeah, so I think it just took about 20, probably 20, 25 minutes. So I'll ask them to, if I go over, they can cut it off. Again, thank you very much to the conference organizers for inviting me to give this special presentation. Thank you. Bye.